for me, it's almost certainly not modifications of gravity and not ordinary matter, like planets or black holes.
Maybe there's some new kind of matter there, or maybe we don't quite understand how things are working. This is always an option for everything.
The preponderance of the evidence is certainly pushing us towards dark matter.
I would say that probably probability that this dark matter exists is close to 100%.
But what makes it compelling is that there's many lines of independent evidence that point in the same place. And in that sense, it's like the evidence for atoms 100 years ago, that what convinced people that atoms existed was not any one line of evidence, but that you had many lines of evidence that all converged on the same conclusion. And dark matter is like that.
So all the evidence for dark matter is circumstantial, if you like, but there are 4 pieces of circumstantial evidence all pointing the same way. So this has got to be looked at.
These researchers think that the bulk of dark matter is made up of a new type of subatomic particle, one that's completely different from the protons, neutrons and electrons that make up everything on Earth. Many physicists think that hypothetical subatomic particles known as weakly interacting massive particles, or WIMPs, make up the bulk of dark matter. WIMPs were initially proposed because they don't interact with light, the fundamental characteristic of dark matter.
A new kind of particle, it seems to just nail it in all the places you see it. And so that, for me, is the convincing thing. So my money is on some new kind of particle.
Axions might also make up the bulk of dark matter. They're very light, having much less mass than even electrons.
It doesn't look likely that axions really could be responsible for this kind of things, because right now experimentally left only very small window where axions could work. Also, it's not so natural prediction of the particle physics.
When you run them through simulation, just putting something like a WIMP in the simulation, you generate structure that does very well when you compare it to galaxy rotation curves and the behavior of clusters and the large-scale structure.
Whether or not the bulk of dark matter is made up of axions or WIMPs, most physicists think that on average, 90% of the mass of every single galaxy in the universe is dark matter.
Knowing that 90% of what's out there is something completely unknown, understanding what that is almost certainly going to change our picture of how nature works in a fundamental way.
Nothing of the physics we know right now can explain it. So there's this real, manifest evidence, like this huge sign in the universe that says, look, there is new physics beyond what we know.
It's a very big open window, and that's how physics works. We always have open questions, and by resolving them, by understanding them, we go a step further, a step deeper.
The universe is like a city at night viewed from a plane. The stars are like city lights, and dark matter is everything else you can't see. So when physicists look at the night sky with even the most powerful telescope, they're only ever seeing a tiny fraction of what's out there. Dark matter isn't just found in distant galaxies. Our Sun, along with the rest of the solar system, is orbiting the center of the Milky Way galaxy. Like all other galaxies, our own seems to be full of dark matter. And so, dark matter particles should be streaming onto the surface of our planet. In fact, if dark matter is made of WIMPs, then millions of unseen particles are passing through your body every second. Over the last few years, physicists have been conducting a variety of experiments to find out if either WIMPs or axions make up the bulk of dark matter. It's been very challenging, since these two particles rarely interact with anything else directly. Occasionally, a WIMP should collide with the nucleus of an atom, triggering a faint vibration. Physicists have set up a number of highly sensitive experiments to detect such vibrations. Unfortunately, cosmic rays from outer space can also trigger the same sort of vibration.
Right now, there are 50 cosmic rays on surface going through your brain every second.
Because Earth blocks most of these rays, many dark matter detectors are located deep underground.
So what we do is we get underground in SNOLAB, 6,800 feet below ground. where the cosmic ray signal is hugely reduced, and it's a much better environment for doing an experiment for a rare event like a dark matter scatter-off.
At SNOLAB in Ontario, Canada, several dark matter experiments are in development.
The main challenge, and it's not only for us, but for all dark matter search experiments, the direct search experiments, is the backgrounds. The backgrounds are particles that we know of, that they are around us, but we don't want them close to our detectors. So basically, we have to shield our detectors from these particles.
One team of researchers hopes to detect WIMPs within a superheated liquid.
We have a gel with millions and millions of small droplets of a freon inside. So when there is an interaction of a particle inside of these droplets, this interaction might put enough energy for this phenomenon to happen inside the droplet. So you have an explosion. So the droplet that's liquid becomes a gas bubble. And we can hear this explosion using acoustic sensors.
Experiments looking for WIMPs are underway all over the world, in the United States, Europe, Japan, and even at the South Pole. So far, none of the experiments has detected a dark matter particle. No physicist has been able to determine if WIMPs, axions, or something totally unexpected is the answer.
Well, science is ultimately about the data, isn't it? And the data will either show dark matter or it won't.
It is a good thing that we really have all these alternatives and that it's in the hands of the observers and of the experimentalists.
Yeah, it's exciting. It's very exciting. It means there's really something there we don't understand yet.
We don't know precisely what is it, but we know what it cannot be.
I think dark matter right now is the best candidate to explain what's going on.
I think within the next few years, we'll have definitely a much better understanding of what's going on. And I really hope within the 10 next years, we'll be able to point down on something.
It's a real opportunity for physics. I mean, it's not just explaining one missing thing in the universe. It's really, once we understand what dark matter actually is, we'll have understood a new, completely new direction of physics. There's no question.
We've come a long way since Vera Rubin first observed discrepancies in the orbital speeds of stars in Andromeda. But we still have a long way to go. Years after her observations changed our understanding of what makes up the universe, Vera Rubin said, "The sky will not be the limit." And she's right. Physicists will continue to look to the skies and beyond until the mystery of dark matter is solved.